Okay, I'm start. Thank you very much. I'm glad to be here and present my presentation. I hope you like it. I'm Andrei Tabakov. I'm from ETU University. And I will present you some of representative of relaxed concurrent data structure. It is a relaxed concurrent priority queue. In our world, in our time, we have real multi-core systems and real multi-core or multi-thread environment. So we could do tasks in exact same time. And it is a problem because we have some shared memory and must do synchronized interaction with that. So for synchronization methods, we usually use locks. For example, like on this slide, we just acquire or release some lock and do not provide an access to another threads. Another way to synchronize it is lock-free algorithms and wait-free and abstraction-free algorithms, which provide you to do any steps of your program, but it will do some useful work in some time. And then we have some transactional methods. So we have a lot of operations, and we could to commit this operation or cancel these operations and do not change our shared memory. So in that case, we need data structures which provide you access to another threads and multiple threads in the same time. This relaxed concurrent data structure is allow you to do this. So this is an advantages and disadvantages. So we have reduced thread contention because we could interact with this data structure in multiple ways. So in the exact same time, we have 2 or more tasks with that data structure. So it is good for scalability and high throughput because we could do same tasks at the same time. And also we have disadvantages of it because some of our multi-threaded execution make changes in this data structure. So we could not expect and we could not provide an expected value in the next step because we don't provide strong semantics for operations. For example, for push and for pop, we have to select one element and select another element because it is in a multi-thread way. So, for example, usual stack, we see that when we do pop operation, we also must select 52 and then 46. It is any time. So we need to synchronize our multi-threaded programs. But in relaxed concurrent, for example, is Kerry relaxed stack, we have some simple data structures which provide you to select not exactly top element, but one of k elements from that. So for this example, we select 46 and 31. So it's not a top element because top element is 52. My work is priority queues. So relaxed priority queues was presented by Alistair, and it is called multi-queues, but I work with it and give some optimization for that. So simple priority queues, relaxed. We have some threads, and we have a distributed queue for each thread. For example, we have 2 queues for one thread. And we want to insert element. So for do this action, we need to select one of these queues, and each core try to lock one of that queues in random way. So it is always randomly, and each thread could interact with any of these queues. So for insert, we have, for example, locked these 2 queues, and we insert elements. So 56 and 27 is inserted in this data structure. But when we have a collision and when two threads try to connect to one queue, so we have some situations when we can't do this action because we have locked it in another thread, and one of the threads try to lock another queue. So for delete max method, we have a similar situation. We need to lock queues. But for improve accuracy of this method, we select not one queue and get top element of that. We locked two queues of that. So it means when we lock these two queues, we could compare its top element and take a more accurate value of this queue. And also we have some situation when we have a collision because it is multi-threaded and it is randomly select a queue. So another thread tried to lock one queue more time, and we have some time for synchronize this queue for do interaction. My work is optimization, so I suggest you to divide these queues into two halves of this queue. So we have not one multi-queue with one entry point, but we have two multi-queues. So it means that first CPU try to lock queues from first half of queues, and second one try to insert element into second half of queues. That's good because we have reduce of cache misses because every thread, every queue tried to cache it in this. And when we have a random access, so it is a lot of queues and we have a lot of cache misses. But when we have reduced these queues, so we try to guess a right value from that queue. So it is an example of implementation. It's a pseudocode for that. So we have first half of threads and try to select it to first half of queues. So for optimization, for delete optimization, we have exact same method. We try to split it in two halves, and that it is. But for that, we have also a problem because we have not large number of queues, because if we have it a lot, we have not good accuracy for that operation. So in one case, we could lock it all. So core 0 and core 1 in the first half could lock all these queues. So to prevent that, we could split it into halves of halves in the quarters. So every core have an own queues and try to select these queues. It also good because we have not a contention between threads. It is an pseudocode of this. And after operations of insert and deleted, we have some situation when one queue have one element and another queue have a lot of elements. So for that, we propose to a balancing algorithm which have some parameters like average coefficient, which allows you to get value when we should do a balance. And also we have a transfer coefficient. It means that we should to transfer some size of elements. And for that we have 20% and 40% for this coefficient. and it's work like that. So we have a max queue and a minimum queue, largest and minimal. Then we try to get elements from the largest queue and put it into lowest queue. So like that. For experimental, we try to experiment it on testbed, which has two Intel Xeon X5670 with 20 cores and 12 cores, sorry. And we have that results. So for blue graph, it is an original algorithm, and for red graph, we have an optimized algorithm. So as you can see, throughput is higher than original. It is for deletion operation. So also we have an original algorithm, optimized half algorithm. So when we split it in halves, and when we split it to cores. So as you can see, the biggest throughput in the last algorithm. Also, we have an experiment in random operations. It is insert and deletion. So as you can see, when we have opt-half insert and opt-exact delete, it is also bigger than another ways of these queues. So for conclusion, we have an biggest throughput for that priority queues. Also, we developed a balancing algorithm. You can see this code into C++ onto GitHub. So thank you.
So we have some time for one. Yeah.
Hi, thank you for the talk. Do you have any correctness proof for your algorithm?
It is non-linearizable, so it is just constant data structure. So yes, it is not correct and like linearizable, but correct as constant.
So you do have a proof?
Yeah.
Okay.
Thanks you for the presentation. Can you tell us what is the increase of memory footprint for your implementation? Which fraction you need more locks to implement this?
Sorry, I didn't understand your question.
How much memory you need to implement this? Comparing to
it's a number of simple distributed queues. So when we have one distributed queue, we have memory for that, only for that memory queue. But when we have multiple, so of course we have a lot more memory for that.
But you haven't measured that?
Yes, no. I'm not measured that.
Because that's important. If we compare performance against what we spent,
yes.
Right? What we lose, what we win. We always want to know everything.
Of course we lose into memory and have some efficient in execution time.
Okay, can you please show the previous slide? There is abrupt reduction of the performance, right, at the 14 number of threads.
Yes, because we have only 12 cores on that.
Sorry?
We have only 12 cores on that SMP node. So it is highest point, and then we have threads more than cores.
So just adding 1 or 2 threads like reduces the performance of your implementation 8 times. Is that okay at all?
No, sorry, I didn't.
When we have a peak performance at 12 threads, and then some other thread comes from some other God knows where and just kills your performance 8 times. How could that be?
Yes, because we have a bigger number of queues, and of course we have more contention between time of thread execution. So we have more threads than cores, and it is problem.
Well, I think this should be researched. That shouldn't be like this.
Okay.
That can't be the big question.
Last question.
Thanks for the talk. As a continuation of the previous question, we know that there is some overhead of supporting 2 distributed queues. Have you tried to play with the number, try 3, 4, and more, and see what happens, regardless the resources we spend to support these structures?
No, I didn't research it.
Okay, thanks.
Okay, thanks a lot. I'm sorry, let's take it offline then. So let's thank the speaker. Okay, so Evgeny Moisenko from apparently Max Planck Institute for Software Systems. Wow. Okay, and the St. Petersburg University.
St. Petersburg University. So I'm from St. Petersburg University and JetBrains Research, and
So it's
other affiliations are
Victor,
for
of course.
for other authors.
Okay, so he's going to tell us about something. The correctness of event structure-based weak memory model.
Yes. So good afternoon. My name is Evgeny, and I'm going to present you our work about the compilation correctness from event structure-based weak memory model. This is joint work with Anton Podkopayev and Viktor Vafiadis. So here is a plan for my talk. So first of all, I want to quickly introduce the concept of weak memory models. Then I will say a couple of words about some particular memory model, that is memory model of C11, C programming language. We will see that this model has some problems. So then I will present the weakest among memory model that tries to fix these problems. And finally, I'm going to tell about the compression correctness theorem from this weakest among model. So first, what is a weak memory model? Well, the weak memory model describes the interaction of execution threads with shared memory in the presence of various compiler and hardware optimizations. So for example, if we will consider the concurrent program shown on the slide, so this program performs some loads from shared memory and stores to shared memory. We can see that this program at least should have 2 different possible behaviors that can be obtained by executing the instructions of various threads in various orders. So for example, if we first execute all the instructions of the first thread and then all the instructions of the second thread, we will get this behavior such that in the end variable A will contain 0 and variable B will contain 1. So I think it should be clear. However, as a result of, for example, some compiler optimizations, the 2 instructions of the left thread could be reordered. This reordering will lead to new weak behavior to appear. So memory models that allows such behaviors to appear are called weak memory models. For a weak memory model of programming language, there is certain trade-off. On the one hand, the model should be strong enough so that the programmers and automatic tools can still reason about it. On the other hand, the model should be weak enough so that the compiler can produce efficient and optimized code. So currently, one of the most interesting memory models, both from theoretical and practical point of view, is a memory model for C programming language. However, it appears that this model is too weak. So let me clarify this on the examples. So again, consider some simple concurrent programs and ask the question whether the weak behavior should be allowed for these programs or not. So for the first program, as we already know, it should be allowed. It's also the case that we want to allow this behavior for the second program because it can be seen as a result of compiler optimization that will remove the redundant if statement and then perform the reloading of the instructions as in this program. However, for the third program, we want to forbid this behavior because it appears out of thin air. There is no reasonable compiler or hardware optimizations that can lead to this behavior. But unfortunately, for some reasons that I do not have enough time to explain here, current C memory model allows this execution for all three programs. So in the recent years, there were made several attempts by the researchers to fix the problems of the C memory model. And one of the recent attempts is a new model called weakest-MO. This model defines the semantics of the program to be an event structure. Event structure is a graph. The nodes of this graph are events. These events could be read or write accesses to the shared memory, or it could also be a fence event. Edges of this graph constitute some relations over these events. And the most interesting property is that the event structure simultaneously contains all possible executions of the program. So again, let's see an example to get the idea. Again, this program, we will build an event structure for this program. So in order to do that, we will execute this program in some tricky way. So we will start by executing left thread. And if we will assume that initially all locations are initialized with 0 values, at this point there's only one thing we can do. We can read the 0 value from the location X. So on the next step, we will execute the write instruction and add the corresponding event to event structure. So that's all for the left thread. Now we can execute the second write thread. And at this point, we have a choice. We can either read the initial value 0 or the value 1. So let's first read the value 1. Again, add the corresponding event to our event structure. Then continue the execution. And at this point, one more interesting thing can happen. We can go back to the left thread and execute it once again, but this time reading different value, that is this value here. Notice this tilde sign. It means that these two events are in conflict. So conflicting events cannot appear simultaneously in one execution of the program. They correspond to different execution branches of some thread. So then we will continue the execution. And finally, we have to execute the second thread again, this time reading the initial value. So that's all. We have built the event structure that corresponds to this program. We can see that this event structure contains 3 possible executions of these programs. One of these execution shown on the slide, this execution, and also this one, the weak execution. So if we will try to do the same with this program for which we want to forbid the weak execution to appear, we can do it. We can also build an event structure in the same way, but this time this event structure will be trivial. It will contain just one behavior of the program. So it forbids the weak executions as we want it to be. So that was the quick introduction of the weakest-MO memory model. In general, for the new memory model to be useful, there are several results about this model that should be formally established. Our work is dedicated to showing the compilation correctness from this weakest-MO memory model to memory models of modern hardware architectures. So in particular, we want to show the comparison correctness to all these memory models shown on the right hand of the slide. In order to simplify this task, we will use the IMM memory model. It is IMM stands for intermediate memory model. It is a memory model that abstracts over some details of particular hardware memory models. And for us, it means that we only have to show that the compilation correctness from weakest-MO model to IMM. By the way, we want to do that, to do the proof in a coq proof assistant. So this coq means a coq proof. So for this IMM model, there's already some proofs done in coq, and our work is dedicated to do this thing. So what does comparison correctness means, by the way? So in general, it means that for every program of the source language, set of its possible behaviors contain the set of behaviors of the compiled version of the program. So in other words, it means that compilation does not introduce new behaviors that was absent in the source language. So just before we are going to comparison correctness proof, I have to say a couple of words about IMM. IMM is axiomatic memory model. It means that it defines the semantics of the program to be not a single event structure, but instead as set of individual execution graphs. So this will complicate our proof a bit. So we want to show that for every possible IMM execution graph of the program, we always can build an event structure such that this event structure will contain the original graph as its subpart. In order to do that, we will traverse the graph in certain order, and we will build an event structure incrementally on the way. So I will give an example here again. This program, on the right-hand side, you can see one of its IMM execution graphs corresponding to weak execution. And we want to build an event structure that will contain this graph. So while we will traverse the graph, we will mark some events as issued or covered. And issued events intuitively correspond to some speculative writes, and covered events correspond to executed instructions. So in order to get the weak behavior here, we have to somehow execute this instruction out of order. So in order to do that, we will first mark this event as issued, and it allows us to add a speculative execution branch to our event structure. Next, we will cover this event, and we will add the event-to-event structure, then proceed, and then we will cover this event. We will add new read event, and that will be in conflict with our speculative execution branch. And at the end, we will cover a last write event. And yes, it is easy to see that indeed the original graph is contained in event structure as we want it to be. So in the conclusion, let me summarize. The first point of my talk was to show you that defining the weak memory model of programming language is a challenging task. weakest-MO is a new proposal that tries to fix some of the problems of C11 memory model. Our current work is dedicated to mechanization of this model together with compilation correctness theorem in the coq proof assistant. So that's all. Thank you for your attention.
Hi, my question again about the price we pay for improved consistency. It's nothing's, of course it can be, more consistent memory model can be made, no problem. Just put locks everywhere and everything is linearizable, right? But what's the price? And what's the price of your solution?
Okay, yes, the one way to fix the model is to make it make it stronger, as you said. But the point is to leave it weak enough so we do not have to pay the cost when we will compile it to, for example, to ARM or Power, and still not make it so weak that we cannot reason about it. So Weakest MO is a model that tries to keep a good balance between these requirements. So it is built in a way that to allow efficient compilation to modern hardware, and at the same time keeping the model strong enough.
Yeah, the reason why you're doing this is clear. You already explained that, but you haven't answered the question. And like,
Then I didn't understand the question then.
what's the price of having this model, which is more stronger? How much slower the program will be? How much, I don't know, more memory it will consume?
Yes,
There's always a price we pay for something good.
Yes, the answer is that we will not pay no price. The problem with C11 is not that the problem with C11 is that it's just mathematically broken model. So, okay, we will not pay.
So there is always a price, always. The weakest memory model is there for a purpose, because it's very fast.
Yes, but
and the performance is our currency in IT. We pay for correctness, we pay for anything.
Yes, and
you
this
will
model
lose something.
This model is weak enough so that, for example, when you compile relaxed accesses in C, in this model, you will not have to introduce some fences or, I don't know, classes, dependencies. It's designed in a way to be compiled with just word and store instructions. So in this sense, you will not have to pay anything.
Okay, but that's wrong.
Did you test your model in practice? For example, did you... Hello, I'm here.
Okay, I see.
Did you patch some C compiler and compiled with your memory model some program and compared to the results of C compiler without your changes? Or it's just a theoretical development?
Currently it is more theoretical work, and yes, it's more theoretical work. As regard to your question, as I said, the problem with C model is that it is not mathematically sound, and because of that, even the optimizations that are already in the C okay, the problem that is current C memory model actually in some cases allow you to define the semantics of the program to be anything. So it means that you cannot do nothing with it when you want to, for example, build some, I don't know, static analysis or model checker for C. You can't do it because the current semantics is broken, and we try to fix it.
Just a note, I think it's not correct to say that it is broken. It's just an artifact. It's just
okay.
It's just an implementation and behavior. It's not broken.
I got your question. We can discuss it afterwards. So because there's a misconnection here, we're talking about different things. I'm sorry, but we can discuss it after. I will try to explain what I mean.
Let's thank the speaker.
My name is Yegor Domakonov, and we keep talking about weak models, consistency, and compilation. So, as Evgeny has stated, there is an intermediate memory model which simplifies compilation correctness proofs. When a language model is compiled into intermediate model, then we automatically obtain a compilation proof for all the major architectures. And in our work, we add another one model to this system, namely OCaml memory model. It's proposed for OCaml multi-core project, hence the name, and its main property is so-called local data race freedom property. It's a generalization of a regular race-free theorem, and it allows to reason about race-free portions of programs. So it worth to mention that both memory models are defined in declarative way. It means that a program execution under such models is represented as an execution graph. Its vertices are memory access events, and edges are relations between those events. For example, you can see that black edges are program order, and green read-from edges are the fact that the read has observed a previous write. And the memory model itself is defined with axioms on such relations. For example, one of OCaml memory model properties is that in execution graph, there should not be cycles made of program order edges and read-from edges. And already from this condition, we can conclude that the second execution graph is not consistent within the OCaml memory model. And as you can see, read values are 1. So we can say that under OCaml memory model, we cannot execute the program above and obtain a result of A equals to 1 and B equals to 1 as well. And we need to slightly adjust our notion of compilation correctness. As it was said, we consider the compilation scheme correct when the set of allowed program behaviors for compiled program is a subset of allowed program behaviors for the original programs. And if we rephrase it in terms of execution graphs, it means that all consistent execution graphs of compiled program should be a subset of consistent execution graphs of initial program. And here's a subtle note. Actually, after compilation, we obtain another graph under another memory model, but actually it doesn't differ too much, so we can use the compiled programs graph to reason about both OCaml model and intermediate model as well. So our goal is to compile it into IMM because in original OCaml paper, there are only compilation schemes for x86 and ARM models, and for example, there is no compilation scheme for Power. And we take the compilation scheme for Power as a starting point. So here you can see the program syntax of OCaml programs. Here we use simplified syntax. And as you can see, there are only two types of operation. It's reads and writes, and only two access modes. Informally speaking, relaxed memory mode represents a regular memory operation, and sequentially consistent operations bring some synchronization to a program. So let's build our compilation scheme step by step. The first instruction, relaxed read, is compiled in trivial way. To show why ARM uses some additional instructions for next for relaxed write, we should discuss mentioned property of the absence of program order and read-from cycles. It can be shown that the absence of such cycles is equivalent to the absence of read-to-write reorderings during the execution. And in order to keep the compilation scheme correct, we need to prohibit such reorderings in a compiled program. Otherwise, the unwanted behavior will be allowed in a compiled program. But ARM, by default, allows such reorderings, so it allows to execute the example program and obtain the given result. But we can prohibit it by using fences, namely acquire fences, which do exactly what we want. They prohibit the read-write reordering. And IMM inherits such behavior, so we can use it in our compilation scheme as well. And we use it in both types of writes. To explain next instruction compilation, we need to explain the multi-copy atomicity rule. It states that all threads observe performed writes in the same order. And this property is partially maintained by OCaml model. So let's take a look at example graph. There are 3 threads and 2 writes. The second thread first reads the first write, and then he performs the second one. The third thread first observes the second write, and then he reads all the value for the variable x. So we can see that those two threads observe writes in different orders. So it's definitely not multi-copy atomic, and Akamo model prohibits such behavior, but intermediate model by default allows such behavior, so we need to fix it. And again, fences come to help. For example, look at this program. There is a relaxed write and the read which observes the written value. Currently, there are no restrictions on program execution, but if we add a pair of fences, then we get the following restriction. Any instruction in a program P1, which precedes fence, release fence, will happen before any instruction in a subprogram P2, which follows acquire fence. And besides other, it maintains the writes observation order. So if we put it in a graph, the resulting graph will be prohibited by intermediate model. So let's use those fences in our compilation scheme. And you see that the fence before relaxed write becomes acquire release rather than just acquire. And let's explain the last instruction compilation. Again, let's take a look at this graph. Here, CO edge stands for coherence order, which is a total order on all writes to the given location. And the subscript immediate means that there is no intermediate write between those two. And FR edge stands for from read, and it represents the fact that the read value will be eventually overwritten with the write value. This behavior is, again, prohibited by Akamo model, since it contains the cycle of the given form. But it's allowed by intermediate model. The difference is that under Akamo model, two threads are synchronized by two sequentially consistent write to the same location. But under intermediate model, they're synchronized by reading from the first write. So we need to somehow force the second thread to read the first write. Let's do it using atomic update operation. It's represented in a graph with two nodes, read and write nodes. And obviously, the read event reads from somewhere. And it can be shown that actually it reads the last written value, which is exactly what we want. Now this behavior becomes prohibited by intermediate model. So compilation scheme remains correct, and it finishes our compilation scheme. Yep. So we have compiled Akamo model into intermediate model. We have proved its correctness in COG, and from this we have obtained machine-verified correctness, compilation correctness proofs for all major architectures. That's all. Thank you for the attention.
Questions? There are no questions. Like my hindsight is not very good. Okay.
I have no basic knowledge of this topic whatsoever. But can you maybe say what's the major difference from the previous work? Like what makes OCaml special with respect to weakest MO?
Okay, let's take a look for how Akamo model differs from the regular C++ and Java memory models. Here is a program with, okay, let's just see how it executes. So what result do you expect with C11 execution? And the answer is, in fact, very easy. You can expect just anything, because there is a data race on first two writes, and the C11 model states that the semantic is defined only for race-free programs. On the Java memory model, things are better in sense that semantics is given to programs with races, but it still doesn't guarantee that after the race has finished, we will observe the consistent behavior. And there are test harnesses which demonstrate this weak behavior. And finally, a camel model guarantees that those two results displayed are the only valid ones. You cannot observe anything else. So a camel model allows to reason about the programs which contain data races. Yeah. That's it.
And weakest MO, where it is here? It's closer to C11?
I wouldn't say they can be directly compared. So it's easier to see the difference between those three models. Yeah. Yeah.
Thanks a lot.
Yeah.
Okay, so now we have the first directly blockchain-related talk in this program by Roland Schmidt. He will present his joint work with Roger Wattenhofer on optimistic ledgers.
All right, thank you very much. So this is my first time presenting any of my own work. Go easy on me, please. Or maybe don't, I don't really mind. So quickly, this is about Byzantine fault tolerance. So let me quickly remind you of what that is. So we have somehow a distributed system with n servers, and we somehow assume that there's f Byzantine servers that are somehow malicious or whatever. And that is traditionally the model we kind of consider for this. And for our purposes, we also assume that they're computationally bounded, so we can use crypto and don't have to worry about details with that. So what usually happens is that those Byzantine servers can somehow present different information in the network, and then creates kind of chaos, because even though you tell each other what you received from someone else, you might still not be able to distinguish who is lying. Like, it could be the Byzantine node that we see from the global perspective right now. It could be any of the other nodes just telling that the other one gave him the wrong value or whatever. And this question asked here is only metaphoric for anything you really want to figure out in such scenarios where you have malicious behavior in your system. And I will maybe give a different motivation as to why it is interesting to consider Byzantine nodes. So maybe a quick history on those BFT protocols. So we've seen some theory yesterday with this guy. I hope you don't mind, I put your photo up there. And we've seen that not everything is just working out perfectly in theory, so we need very specific circumstances so that we can achieve stuff like consensus. And then there was a huge step forward towards designing more practical systems when people said, okay, let's get away from the asynchronous model, which maybe is not super realistic anyway. And they defined a so-called partially synchronous model, which you have seen in one of his exercise statements yesterday. So that's like assuming there is a bounded message delay, we just don't know it, or assuming a bounded message delay that we know, but it will only eventually hold in some future. And in this model, most of the systems that are currently being designed are usually set up. And I guess the most prominent and first one to be really successful in practice was so-called PBFT. And at this point, I think there might be a big argument whether the statement I make here is correct or not. I'm kind of saying this is, for me, the original fast-track protocol in a way. I mean, just try to accept my perspective for this talk, and I'm happy to discuss this later. Maybe this is just flat out wrong, but I would somehow claim that PBFT tried to say, okay, we make somehow optimistic assumptions, and then we design a system that works well in those assumptions, but still gives us safety guarantees for the very worst case of an asynchronous network. I totally agree with those assumptions, because an asynchronous network is just not what we experience in our internet in everyday life. Right? We have TCP, we just re-emit messages. We can kind of guarantee that after 5 minutes we should have a message through, unless the node really crashed. And when the node really crashed or is somehow off in a network split, then maybe we can somehow figure out to put this into the Byzantine fault tolerance guarantees of the 1/3 nodes that can fail. So where did we go from here? There's a few optimizations that happened from there. So Sysiwa was like the first protocol to introduce an optimistic fast track from there, assuming that there is not even any failure occurring at all. And saying, okay, in this case we are super fast. I'm aware that there's some doubt that it's correct. So I've also put SPFT here, which supposedly is doing that correctly now. And so we have an optimistic fast track there. Another thing that kind of came in mind was that PBFT had a leader change protocol, view change protocol that was quite costly. And people said, okay, look, maybe if we just incorporate that in our protocol, we can somehow avoid that overhead. And another thing that recently came out is the idea that if we want to design something like a permission blockchain anyway, where we have several blocks that we chain along and we have several steps in our pipeline, so to say, anyway, why would we do 3 separate rounds of committing stuff for each of those blocks if we can just somehow defer the commitment of a block to a following child block or a grandchild block? And now I finally come to work we did, saying we try to combine those ideas that we've seen here and put some new touch to it. So we would kind of argue that we try to build a Byzantine ledger. So developing a ledger for an optimistic case where we just don't allow any failures to occur, or maybe only a constant number of crash failures, but nothing else that could go wrong. That was just not what we wanted to do. Yeah, so usually those fastpaths, they assume, like fastpaths, that's those optimistic cases, they assume that there is just no failure. SYSIBA, as I mentioned, or SPFT, they assume that there is no failure or almost no failure. SPFT having like a constant number of crash failures being tolerated, but no Byzantine failure. So how can that be a BFT protocol with the selling point being fast in a case where there's no Byzantine failure? So yeah, in those cases, with those fast paths, it's kind of easy. I mean, if there's nothing going wrong, then you just have one node deciding and it tells all the other nodes what we will do. Yeah, so our interpretation of such an optimistic case is slightly different, and we therefore define the term optimistic latency in the way that we say we count the number of message rounds that we require to get a commitment of new transactions, of new requests into blocks. When the network is somehow synchronous, so when we don't have network timeouts occurring, or maybe some of them, but somehow covered by the Byzantine fault tolerance guarantee, and maybe also like the node that is currently selected is also not malicious. I mean, otherwise we just change it to a node that is not malicious. But we want to be fast in that case. Other nodes can be malicious. And then we came up with this table kind of saying this is the evaluation we get. The optimistic latency is this point. Maybe it's easier if I just point to it. And then we see that PBFT was actually doing quite well in this model, because that's kind of the normal operation case they have considered. And this is like the one big result that has been standing there for 20 years now. The other things like SYSIBA breaks down as soon as there's a crash failure, Tendermint is just like PBFT, SPFT has a problem as soon as there's Byzantine failures. Hot stuff, for fairness, I have to say they're optimizing for something very different. So they're clearly the best back on this side, right? They're optimizing for the case, basically optimizing for the throughput with their pipeline model. And Pala we just mentioned because their ideas are rather similar to ours, except for this optimistic path. And now I want to give you a very brief overview of how we claim to achieve that we get an optimistic latency of only 2 round trips, not 2 round trips, sorry, 1 round trip. So it basically happens as follows. Usually, I said, leaders are elected and get to decide what happens and tell everyone else. In our system, everyone else tells the leader what they're allowed to do. And that's why we call it permit BFT, because everyone issues a permit telling the leader what it is allowed to do. Basically, we build up a block graph structure, like a DAG of blocks, and we specify in those permits where you're allowed to create a new block. And the only thing we need to agree on is where in the graph you are allowed to append a block. If you acquire enough permits for that position, you're allowed to create as many blocks at that position as you want. Obviously, an honest node wouldn't do that. It would create 1 block. A Byzantine node could create any number of blocks, but what's the power of this? Well, if some honest node created a block and somehow there was a timeout or whatever because the network currently does fail, and the next honest block would have acquired enough permits to create a block at that same position, we would get a fork. And we would handle those situations with the same kind of guarantee as we handle the situation that a Byzantine leader decides to create multiple forks, or multiple Byzantine leaders decide to create forks there. So the basic idea of the protocol depends on the fact that we say we don't accept any new block, but we only accept blocks that have child blocks. Basically saying as soon as there's a block and enough people voted on appending to this block, that means enough people have seen this new block and have told a new leader to append to that block. For the safety guarantees and that stuff, I will have to refer to the paper today or to discussions with me later. I'm stoked if anyone is interested. So let's have a quick run through of what might happen. Say this leader has acquired enough permits to create a block. It sends its block to all the other nodes. And then maybe the next leader is a Byzantine leader, because we also do that round robin scheme currently. Thinking about how to get rid of that, but currently we still do that. So what can a Byzantine leader do, even though it acquired enough permits to create a block? Well, either it can create blocks, right? It can create different blocks like B and A, right? It can send both of those blocks to its coalition partners that are part of the adversary. And it can simply leave out some of the nodes. Basically, this is the scenario that we kind of exclude in our measure for optimistic latency. Just to see what happens in such a case and how we handle these cases, well, in case of a timeout, someone would ask, hey, I've got a timeout, like, what should I do? And then either the other people also incurred a timeout. That would kind of mean that this person is probably crashed, right? So we would just go on and give permits to the next leader, or the others would simply reply with the block they've seen, and yeah, then you can issue permits depending on what block you've seen, and the protocol just goes on. So basically saying a Byzantine leader can, in the worst case, influence the protocol up to like this point, and this one kind of unifies everyone again, and the next honest creator will be able to issue a new block. So this may be already the last slide almost. So this is the case where I argue that I really only need 2 message rounds from the moment that a request arrived to the moment when I can send an acknowledgement back to the client. Why is that the case? Well, you might have noticed that I said and emphasized before, the permits do really not depend on the content of the blocks at all. So I can collect the permits to create a new block already before receiving such a request. The idea being that as soon as the request comes in, the block creator can immediately issue a new block, send it to all the nodes, and as soon as all the other nodes have confirmed this block, or not all of them, but 2f plus 1 of them, which is n minus f in the speech of yesterday's talk, this next leader can already send the acknowledgement, and that's how we kind of achieve this optimistic latency. All right, maybe I was super fast and unclear at many points. I'm happy to take any questions. Maybe 2 things I wanna emphasize. What is the main thing I'm interested in discussing here? I think the details of the protocol are something that is basically best read in the paper or discussed with me in like an offline session. What I'm most interested in is, do you think it is a good idea to consider other realistic models, or to argue for more realistic models in theory? Because I feel like in this domain of BFT protocols, we kind of have that split between the real plain pure theory, which is Byzantine agreement, and focusing on hard models like asynchronous models and all that stuff. And I kind of feel like I want to use theory by mathematical thinking, as we've seen it in the presentation by Professor Lemper yesterday, and design systems that are somehow usable for practice, for real-world applications. And my feel is that we need a model that really encapsulates all the circumstances we have there in practice. And yeah, that's what we're trying to get to. And yeah, the other stuff, whatever. Stay optimistic. Don't just think about the saddest moment whenever there's a BFT talk. Right. Thank you. Sure.
Hi, thank you.
Sure.
I've got two questions. First question is, how do you manage, if you can show the previous slide, please.
Yes.
Yeah, how do you manage that all permits come to the one node? Or what's in the case when several nodes have permits
So
at the same
that case should just never happen. Basically, what happens is that we go round robin. So you kind of have a global ordering of all the nodes that they know from like a Genesis block. And then the first node just gets permits to append from that block. And as soon as it issues a new block, all the other nodes will go to the next leader. And there's a global total ordering that is known to everyone, and you would just go round robin in that order.
So it's like fixed amount of nodes.
Exactly. I mean, you could always argue that you can like make transactions on the blockchain to change who's participating and so on. But we currently more interested in building a functioning system first and then making it dynamic for practice. Yes.
Yeah, I see. And how fast do you expect this to be in terms of 3 times faster, 10 order of magnitude, million times?
That's a good question. So my expectation to this is kind of very fuzzy because I did not manage to have any evaluation on this yet. So there's no implementation. There's a very, very tiny simulation that runs on like one computer and really literally only simulates being in a network. And I mean, it simply works that you have commits after one round trip time. As long as that works and you don't really have a Byzantine failure, which is hard to simulate because it's an arbitrary failure, right? As long as that works, it would obviously be better than a protocol that requires a longer latency. But I can't really make a statement about anything else right now. Yeah, I'm hoping to get there in the next year.
I have a question. So if I ask you to, in 2 sentences, say what's the feature of this speculative protocol compared to like a magnitude of protocols proposed recently, in particular to hot stuff, which reminds very much this one. So what would you say?
What's the feature of this? I would say basically we're inverting the process and giving a new take on thinking about that the process of creating a block. So usually we always had the systems kind of proposing something and then accepting that something. And we are really trying to separate the powers of what you need to be able to do as a leader as far as possible. So we really restrict the leader to be able to only do what we allow it to do up front. And by that, we finally achieve a protocol where you vote on a single request only a single time until it's already committed. And hot stuff, I would say, is very different in that, I'm lacking the words. Yeah, I should have prepared for this question directly, right? Sorry, where was I?
You starting talking about hot stuff. So
basically with hot stuff you would get basically just a throughput optimization, and this is very much optimizing for the direct latency, right?
Latency, yeah.
So this is the main difference to hot stuff. I would agree that it's very similar. I mean,
does it mean that you have lower throughput? You would get lower throughput?
I can't answer this ad hoc. I probably would get lower throughput than hot stuff,
well,
yes.
I would just presume because you
Yes, no, I would assume that because we get like one extra round in this case where we have an honest leader. Where was it? Sorry. Here. In this case where we have an honest leader, hot stuff can simply make progress there by creating a new block, which will be committed probably just 4 blocks later. And I cannot create a block in this moment because so it's basically a trade-off saying when do I consider a block committed and what can a leader do. Yeah.
Okay. Well, right. Thank you very much.
Thanks.
So Alexander Visharadin is going to present the last student work at this program, and it's going to be about efficient cloud-based storage.
Okay. Thank you very much. My name is Alexander Visharait and I work at ITMO University, and today I will talk about more applied questions and more applied solutions than previous talks. And I will tell about our joint work with Siemens and how we created a high-performance numeric time series database. Okay, so what was the motivation of our work? Why did we need to create yet another time series database? And the main reason was that there were some requirements which we had to meet, and other solutions couldn't do it. So the first requirement is we needed to store terabytes of time series data with the time span of tens of years. And it was already a challenge for some minor databases, but still we could do it using some mature, well-established databases like PostgreSQL or Cassandra. Another requirement was that we needed to perform conditional search and data extraction. It can be made in any good database also. We needed to perform all requests, both search and extraction of 400,000 data points within 1 second of time, and it is already a bit harder. Because of data volume, and we saw that timescale or ClickHouse with materialized views could solve this problem. And the fourth major requirement was that all data must be stored in cloud storage like Amazon S3, and none of existing solutions could fit this main requirement. So two main major use cases for our solution was that we need to browse a lot of data. So basically we need to work with all the data which we store, and it must be easy as that. And we must be able to zoom in, zoom out from years to hours and minutes and maybe seconds for high frequency data. And another use case that we needed to search, for example, search for anomalies in our database. And it also was very prominent use case for us. So what was the result? So what we achieved in the end? We developed a Peregrine, which is a binary storage, basically. And it can perform complex search requests within hundreds of milliseconds of time. It can extract up to 15 million data points per second on a single node. And it can ingest data on the speed of 8 million data points per second. We have very good data compression, and we can sample data, we can aggregate the data, and we can transform the data, for example, compute moving averages and other things. And our index is very small and compact. For example, for 1 billion entries, it weighs only 1 megabyte. And it can easily be extended for new storages, new metrics, new aggregations, new transformations very easily. So, current cluster schema is quite simple. We have only one entry point, which is manager, and it redirects all requests to the proper nodes. For example, other two types of nodes are indexer nodes, which are responsible for data ingestion, data deletion, and modification. And worker nodes are stateless nodes, which were designed to make possible performing extraction requests, which are very heavy requests, the heaviest request in the database. And these nodes perform only extraction, and there can be a lot of worker nodes which can perform these operations. So how do we create this lightweight and powerful index? We split all our data into so-called data parts, which are basically a set of pairs, time and value. And we extract some metadata from these data parts. For example, data size, number of elements. We compute all statistical characteristics, which are metrics here. And we compress or not compress our data for the sake of speed of access or compactness of the internal representation. Then we combine blocks into segments for easier and faster search operations. And all segments are then combined into index. So we have one index for every sensor which we store in the database. So it allows us to perform absolutely independent operations for all sensors which we store in the database. It is how we build our index. And the other thing, we need to convert our data itself. So we calculate index, and on the next step, we create our internal representation. And internal representation is also created from data parts. So we extract some characteristics into the blocks, and after that we encode every data part into binary data array. And after that, so for every block, we create one binary array which contains compressed or not compressed internal representation of all the data. And after that, all these independent block slices are combined into one single segment data file, which is stored in the backend storage. And for storing and for creating internal representation of the data, we store time and values one after another for every data part. So in data part we have time value pairs, and in the internal representation we also store them like time value, but not time and value. We delta compress them, and timestamps we compress from 8 bytes to only 4, because we calculate small deltas between timestamps. And for values we calculate not deltas between floating point values, but we convert them into their binary representation and calculate deltas between them. It allows us to have longer zero sequences, which can be compressed much better. So after that, we, depending on the configuration of the storage, we can compress or not compress these sequences of data using the standard algorithm. So to allow users to extend our storage, we have specific interfaces. So interfaces are just programming interfaces which user or client can implement and allow our storage to work with their custom, for example, storage, backend storage like Amazon S3, Google Cloud, or distributed FS like HDFS. Reader and writer are interfaces for reading data from client and for writing the data to the client. For example, we can read data from CSV and Parquet files and write them in JSON or also CSV formats. And metrics are aggregated characteristics which allow to calculate some, for example, standard deviation, minimum, maximum percentiles, and we can perform searches on these metrics, and we can extract the data by calculating metrics and values for them. And the transformations allow us to transform data while we extract them. For example, we can calculate differences, moving averages, and other things. So for experimental comparison, we compared our developed storage with InfluxDB and ClickHouse. And first, we compared these using dataset of 10 billion points. So on the first experiment, we compared how fast can our solutions search the data. And we saw that Peregrine outperforms both solutions by orders of magnitudes. And when speaking about data extraction, Peregrine DB is like 20 times faster than ClickHouse, for example. And other thing which we wanted to experiment and to investigate is so we can work with Amazon S3, which is a good binary storage solution. But would it be faster to work with distributed and distant solution? Would it be faster than working with local EBS storage? And our experiments showed that in many cases, especially when we work with really a large number of requests, Amazon S3, because it has no limitations, artificial limitations by Amazon, it can be much faster for being backend storage for the Peregrine than EBS storage, which are placed locally in the system. So currently we are working on improving availability and reliability of the system because it has some sloppy edges at the moment, and we are working to eliminate them. So thank you very much for your attention.
Thank you. I have two questions. First, did you measure what a time between ingesting one document and reading after that? I mean, time after it available for read.
It is available immediately after ingestion.
Okay, and second question about storage space. So you compared Influx, ClickHouse. So what about space needed to store that amount of data in that databases?
I do not have exact numbers, but Peregrine has the lowest required volume of data for storing. So it is close to InfluxDB because Influx is specifically tailored to store time series data, but it is much more compact than ClickHouse.
Okay, thank you.
Oh, okay. There was an N letter on your slides stated for number of TV pairs, timestamp and value, which you aggregate in simple data part.
Yeah.
How do you choose that N?
How
you choose that N?
Oh, it can be configured on the level of storage. For example, if we know that we store only data, for example, with the frequency of 1 Hertz, not so frequent data, we can predefine it in the configuration, or otherwise client can set size of the blocks and segments in the request.
So you rely on size, not on frequency directly?
Blocks and segments are created by time size. Yeah. For example, blocks can be of a size 1 hour, 2 hours, or 10 seconds. So we split data by time, not by size.
Okay. And the second question is, will your clients be able to add their own metrics?
Yeah.
And what requirements are on these metrics? They must be additive?
No. So basically, to implement any metric, you need to just implement the interface, which is some programming interface with 1 or 2 methods. So, for example, standard deviation is not cumulative metric, and so it cannot be calculated as we add the data. And for example, minimum and maximum are cumulative, so they can be calculated. And it depends only on your implementation of the metric.
Okay, thanks.
Yeah, thanks. The results really look promising, but I think the comparison is not quite correct in terms of you just said in the end that availability and fault tolerance things are not quite defined, right? Or not quite complete. So if we compare performance, we need to understand in which fault tolerance model it works, what is the availability model of both things you compare, right?
Yeah, but basically, the main thing which Peregrine lacks at the moment is data replication for local storages. So in cases if we store the data in Amazon S3, so we basically do not need to replicate the data because it is already in the Amazon S3, so we do not replicate the data. We need only to replicate indices across the nodes, and it is already implemented at the moment.
I see.
Maybe I missed. Could you please add more information about the readers that you support? For example, some readers compatible to visualize this data in some systems like Grafana and see this time series data.
And could you please repeat the question? I can't hear properly.
Well, my question is about visualizing the data you store. For example, FluxDB supports some readers that export the data for Grafana that can visualize.
Yeah, we have our internally developed plugin for Grafana, so we already support, so you can visualize data in Grafana from PeregrineDB. Yeah.
I see. Thank you.
Are there any more questions? Okay, let's think this. Okay.
Just a quick one, sorry. Thank you for the talk. I'm just curious, how did you settle on this particular kind of delta compression technique, and whether you consider any other ones, and also how does that interact with basically storing anything other than IEEE floats, if that's possible at all?
So we experimentally found that at the moment delta compression is the best method for us. Maybe if in the process of developing we find some alternatives which will work better, we will consider them, but at the moment we are not planning to choose between other ones.
Okay, well, let's thank the speaker.
Thank you. My name is Yuri Kuznetsov. I work at Siemens. I joined Siemens a few years ago. Siemens is known for manufacturing big machineries like turbines, trains, like Sapsan train that some of you might used when traveling to St. Petersburg from Moscow. Well, we also at Siemens have great moves in terms of R&D work, and I work personally at the corporate technologies department of Siemens, where we actually, what we are doing is R&D by itself. In a few words, we are serving the industrial units of Siemens. We are finding some innovational solutions to their problems, be it hardware or software. And the R&D activities that we do go beyond the boundaries of Siemens, and we do cooperate and collaborate with universities. This is what Siemens is doing around the world, and particularly we are doing that in Russia. And today I will talk a little bit what we are doing and how we turn the investments and human power into innovations, and what could that mean? Well, actually, whatever you see here, there is a separate story behind every activity we do with any of these universities. It can be studied case by case, and different people stand behind every story and so on. But in large strokes, our probably main counterparts are ITMO University in St. Petersburg and Polytech at St. Petersburg. There are also other labs and universities we cooperate with. Today I will talk a little bit with more details about ITMO and SPBPU and Polytech and the projects we are doing with them. So our, the most visible result of our cooperation with ITMO is opening an R&D lab, which is called Industrial Cognitive Technologies. We opened it in March this year. We do projects. We actually continue doing projects with them. We have a team of people there. Alexander Isharatin was one of them. And the research directions are the high-load streaming data processing, industrial data storage, conversational UIs, a few words about that later, and even a graphical user interface innovations, can I say. Actually, a few words about this data processing and the sensor data processing and the topic that was just before me about Peregrine. In Siemens, we do a lot of manufacturing, hardware testing and everything, and hardware maintenance. And hardware maintenance means monitoring it. So a big part of work of Siemens engineers is about just knowing how these hardware behave, how to measure it, performance, and we use sensors. Sensors produce data. Data in vast amount is reaching some systems where it needs to be stored, searched, and analyzed. So this is why data, or sensor data, is a very important topic in any collaboration that we do. Well, with Polytech, it's a little bit different. The lab is called somewhat similar, but still is different. It's called Industrial Artificial Intelligence Lab. We have empowered Polytech's computer center with NVIDIA DGX-1 supercomputer, which is specially designed for machine learning. It's got like a petabyte of flops. Well, also what we do with Polytech, we have scholarship programs. We'll not speak about that, it's just a separate story. And we also do semester projects with magister students, and we also give them some awards if they perform well. We do have some other activities with other institutions around Russia, in Kazan and in Moscow as well, but I don't really know what they do there. So back to what I do now. With ITMO, the most highlighted projects, I would say, would be the Peregrine. Alexander told about that. Just a short introduction about that. The prerequisites for Peregrine were real problems they do have in business units of Siemens, for example, in the unit where they store and analyze sensor data from large gas turbines. And the problem they have, they actually migrated a few years ago into the cloud, into Amazon. But the thing is, they started with using services that were promoted by Amazon, which appear to be very expensive. They are very good at performance. They are massive parallel solutions, distributed everything, but they're really expensive. Tens of thousands of euros per month. This is the price of using that services. And that is a good prerequisite for us to continue working on Peregrine, although the idea of Peregrine came before that. So that's why we see potential of Peregrine, although I admit this is kind of a niche database, but still a lot of interesting research can be done there. Other topic is a family of projects dedicated to time series processing under high load, searching time series data, for example, searching it by pattern. This is a typical, not typical, but a demanded use case that we have from some business units in Siemens. And another, last but not the least, interesting topic is the one that we started last year after we got in contact with Siemens Healthcare. This is a former business unit of Siemens, but still is called Siemens Healthcare. They brought us a lot of interesting ideas of the projects, and one of them is doctor's digital assistant, where we need to build a system with a dialogue interface where a doctor can either speak or chat with a bot that will help him to tune his hardware. Siemens Healthcare's business is mostly about producing the hardware, like tomographs, MRT machines, all these very expensive and complex machines. And the doctor often needs assistance in configuring it for the next patient who comes. And this is where the digital assistants can help. This is not just taken from out of nowhere. This topic was proposed by one of the workers of Siemens Healthcare, he really sees a demand for that, and he thinks this will be a very useful thing. Well, then to Polytech, what we have there, in Polytech, we have one great advantage. The people there have experience in doing hardware prototyping. That's why we came to this idea of a project with technology innovations for dairy farming. It's a business where people make milk out of cows. And actually, we have good progress here, and we designed wearable sensors for the cows. It's not something really new. Many companies do this, but we do this by ourselves, and we design each and every aspect of the hardware. And then we also build a system around it that collects the data from these sensors and can analyze it. And well, we actually have, the most interesting thing is we have a test set up at the real farm. We actually visit it regularly. We install the hardware. We connect the software to these cows. And I will show you a short video. Or actually, I can do this while I'm speaking. I'm finishing my speech. This short video actually will play in a loop. It was made in winter time at this particular farm. You can see how it looks like. It's really, I have nothing to do with this dairy farming, neither Siemens has or had, but now you see we just have our new partners there with 4 legs. Well, while this is playing, I will complete my speech with another challenging project that we are about to start. This is about rapid prototyping, whatever it means, with machine learning. So the domain for us is the industrial design of parts of hardware that Siemens manufactures. Because manufacturing means designing, testing, then producing for the customers. That might be parts of turbines like blades. For example, the picture you can see is a blade. This is a small part that is installed on the rotating part of a turbine, and that works, that actually makes mechanical work to either rotate or produce power from condensed gas. Anyway, this is a challenging task, and engineers spend a lot of time on using this CAE software, computer-aided engineering software. And there's a lot of optimization work done or needed there. And we indicated some steps that can be speeded up considerably using machine learning techniques. But for that, we need to really know how to model many complex processes using modern techniques like deep learning or whatever. And we do have, how to say, our supercomputer there that should be used for these tasks. So this is how we do what we do with our investments that we can spend with the universities. And I would say, for me, this is actually always learning, because it's not that we make an investment, then we have people, and the project starts and goes. It's very tough, actually. And maybe the last message from my side would be, and I would ask if anybody can share his experience with that, is this. So what drives you in your R&D? Because the motivation, as I discovered, is probably the most deficit in this domain. What drives people, why they are doing this R&D? Were they asked to do that, or are they really inspired by something? And so I'm trying to find the answer to this question, and by doing projects with many universities. Well, if you have answers in particular questions, I can answer after my talk. I can show you some other interesting materials. So, but I'm finished. If you want, you can ask some questions.
Questions? So what can you say anything about job openings in your lab?
Well, the positions at lab are not managed directly or paid by Siemens, so this is rather up to the universities. What we are looking, or who we are looking for, are data analysts and people with good knowledge and experience with deep learning. This is what we're really seeking for at Polytech projects. I'm ready to talk about opportunities that you might have with us or with Siemens, because it can be anything. You can either start working at the lab, or you can start working with Siemens or in Siemens, I don't know. Well, this is generally it.
What's your answer to the question about motivation?
The motivation. Well, I can only answer for myself. Like 15 or 20 years ago, I was wondering what would be. I was thinking I will be at the university side, and I will somehow collaborate with industry, but it turned out the opposite. Somehow I went from the industry side, and I see how difficult it is even for the company. What motivates, well, apparently turning what we have already from science, from computer science and from software world, turning it into some result that you can touch and you can say you did that. For example, with these cows, you can say we improved the production of dairy farming just because we can monitor and predict the diseases of the cows, or we just shortened the path of these products into the market with these blades. I would say, okay, yesterday when I was listening to Leslie Lamport, I also came to the idea that what motivates me is the number of surprises I actually get during my work here, and I have a lot of surprises here. I didn't think it works this way, but I found it does. Whatever it concerns about cows or databases, time series search, whatever. It's about surprising, and that's what motivates me.
Okay, so thank you very much.
Thank you.